Hi, everyone. Welcome to the IRRICAD webinar series. Thank you very much for joining us. This will be our second webinar in the series. I'd like to introduce our team. My name is Graham Hutchinson. I'm with Nelson Irrigation here in Walla Walla, Washington. Mike Noftel is an independent consultant in Washington State. Steve McCoon is with Nelson Irrigation here in Walla Walla also. Jo Vivier is in New Zealand with Lincoln Agritech, the Aircad company. She is the global support person. And Ignacio Del Campo is with Nelson Irrigation, and he is located in Chile. We're here to help you. So today's topic is elevations, and we will be discussing some concepts. We will be talking about some definitions, some important settings within Aircad, and demonstrating various methods to draw or import elevation data. Please use the question and answer feature within Zoom to ask questions, and our team will try to answer you during the webinar. Para los asistentes de habla español, se puede hacer preguntas por el menú Preguntas y Respuestas. Trataremos de contestarlas en español. So one of the first things that we'll discuss is what is a geo-referenced object. Naturally, elevation data has location information along with the elevation data. The elevation data belongs to a point on the ground. And many sources today to obtain location and elevation data are geo-referenced. A geo-referenced object has location information that describes exactly where the object is in the world. If you give this information to someone, they will be able to find it, even in the fog. This sounds simple, but determining the location on Earth can be complex. The world is a sphere. It's an irregular sphere with a lot of bumps on it. And that mathematical models exist that create a geographic coordinate system. WGS-84 is a world geodetic system. It's a mathematical model, and it creates a coordinate system of latitude and longitude. It's difficult to describe a square or rectangular field using latitude and longitude, and most CAD software works on a flat grid, not on a sphere. So geographic coordinate systems are further modeled by what is called a projection to flatten that data into planar coordinates of X and Y with Z values for elevation. The UTM projection is used within Aircad, and it is Universal Traverse Mercator. It's a common projection model. So there are options for both mathematically modeling the coordinate system and applying a projection to obtain a grid. These are the ones that Aircad uses. What this really means is that we can take global information, we can import it into Aircad, do a design, and then we can take that information and take it back out to survey equipment to peg it in the field or locate everything in the field, locate the valves and the pipes and the sprinklers. The key in this is to use the same translation system coming into Aircad and going out of Aircad. If you use different systems coming in and out, things won't end up in the real world where they should be. So UTM, the UTM system creates coordinates, but you can't flatten the Earth into one great grid. And so the world is divided up into UTM zones. And these are the UTM zones around the world. And it's important to think of that, for example, the coordinate 5,000 by 5,000 exists in every one of these zones. So you might have an importation that has large coordinates and are UTM coordinates, but if you don't have the zone, then you really won't know where it is in the world. Usually the UTM zone is imported with the data. Sometimes it's not. It's something to keep an eye on. Here are the UTM zones within the United States. And when you import data, particularly from Google Earth, the UTM zone will come with it, and you really don't have to think about that. There is a setting within IRRICAD that we will look at, and we'll mention the times that you do need to use it. Another thing to keep in mind is that for a given latitude and longitude, or for a given UTM X and Y, an object might move over time. So if we locate this post, and let's say we established the coordinates late last year in 2020, in 50 years' time, that same latitude and longitude or X and Y UTM value may be in a different place. And the WGS 84 maintains latitude and longitude, and the Earth's plates may move, and so objects move with them, and they may not be in the same latitude and longitude. Some mathematical modeling systems, for example, the North American Datum, NAD, which produces the state plane coordinates, they have fixed points in time. And that's an example if you try and merge information coming from state plane coordinates with download from Google Earth, then it's likely they won't match up. And Joe was going to cover importing things from different datums in the presentation on Monday. One last thing before we go into IRRICAD and look at some different methods is it's worthwhile paying attention to units. Some importation processes bring units with the data. Some importation processes are unitless, and you don't know the units. They just have coordinates of X and Y with elevation and Z. Often there are several steps prior to importation. It's important to check the end result. As an example, I recently received an AutoCAD file that had originated in the metric world with survey equipment. And so the survey was done in meters. That was imported into AutoCAD, where the default units must have been left as inches. And so that was worked with, and then I received that file and imported it into IRRICAD. I knew it came from the metric world, so I had IRRICAD in meters. But because it had gone through AutoCAD with default units set to inches, the scale was off by a large factor. And often there's no breadcrumb trail of units when files are migrated through various software. So it's something to check when you import things to make sure things are to scale. So now let's jump into IRRICAD, and we will look at some different methods for importing data. Here's an IRRICAD screen, and I have a rectangular field there. And so one of the first options in creating elevation data is to draw it in. And so what I'm going to do is to draw some spot heights from the draw menu. And I will put a spot height here, and let's say I will give it a reference point of 100. I will put another one over here and say, I know that there's 5 feet of fall down that boundary. Let's say I'll put one here, and I know that there's 2 feet of fall from the top left to that point. And maybe down here, I know that there's 7 feet of fall from that top left corner. And let's say approximately here, there's a little a rise 2 feet above. So we have some spot heights in there. What we can do now under the Tools menu is to calculate contours. Would you like to create a DM model? Yes. And in this window, you can see if we set the contour interval to 10 feet, there is one contour. If we set the contour interval to 5 feet, there are 2 feet, there are 4. I'll set it to 1 foot, and there will be 8 contours drawn. Mark as calculated means that they will be drawn and you won't be able to change them later. If you remove that check, you will be able to edit the result and change the elevation of the contour. There's a pop-up message saying it's less than the minimum. I think the minimum might be 0.5 meters and 1 foot is less than the recommended 0.5 meters, but we'll say okay. And so now we have a series of contours. I'm going to draw, let's say, some zone pipe in this field, just to give people an idea of pipe. And I'll turn the junctions on so you can see the different junctions. Now I'm going to show what we call the digital elevation model. And this is a model of the surface of that area. If you hold the shift key down and scroll your mouse wheel, you can expand it, and then you can rotate it. And it gives you an idea what the area is, and you can see, well, does that look right or not? And it looks right. So we'll explore a little bit the significance of this digital elevation model. And we'll go into the design parameters and look at the analysis parameters. So in creating this model, IRRICAD has taken the width of the elevation data, so the distance from the left to the right of the elevation data, and it has created 500 different points across that x-axis of those elevation data. So if there was a distance of 500 feet, behind the scenes, there would be a point every foot, and the digital elevation model would interpolate the elevation at all of those 1 foot points. It uses the same interval between the x points and the y, and so it goes vertically, and it creates a grid of a lot of points. In this example, there could be 2,500 points behind the scenes, and that's what it uses to establish the digital elevation model and the surface that you see here. The accuracy number, and you can set that as different values. I think the default when IRRICAD is installed is 500. If you set it to 0, IRRICAD the process will determine what number of points might be a good set of points. For the moment, I think leaving it at 500 is good. If you're dealing with a very, very large area, perhaps miles or kilometers in width, you may want to increase that to increase the resolution. The accuracy, the process calculates the accuracy between what the elevation is on the surface model and a point that it used to calculate the surface model. So here we have a point here, and the process will determine the accuracy, the difference between what is on the surface model and that point that it used to establish the surface model, and you can set the required accuracy here. Also, a thing to note is that when IRRICAD interpolates the elevations of pipes and valves and objects within the design, it interpolates them from this surface, from the digital elevation model. It does not interpolate the elevations from the contours or the points. The points were used to create the contours, and the points were used to create the digital elevation model, and that was verified with an accuracy. However, the elevation of the junctions and valves is interpolated from the surface model. So let's turn a few things off here so I can just have the elevation information on screen, and I'm going to delete that and then turn everything back on. Another way of describing elevation information is to draw contours. And so we can draw contours, and let's say that we know that, for example, it's flat across in this direction, and we can set that, say, to 100. And we know there's a certain slope, and that slope results in an elevation at the bottom of 90. And let's say we can draw a point here because we know that there's a small rise here, and we can say that that's 102. And we will produce our elevation model again. And we have a slightly different elevation model. I'll hold the Shift key down with the scroll wheel just to exaggerate it, and we can see that things look in order. There's one other parameter in the settings that we can adjust. This elevation model was created by contours and created with a point. Under the design parameters and analysis, we can see that there's a resolution here of 15 feet. And really what that is, the digital elevation model is not created from the contours. What it does is it creates points every 15 feet along these contours, and then uses those points plus that point there in order to create the digital elevation model, the surface. So that particular setting there places points along the contours behind the scenes at 15-foot intervals, and that's something else that you can adjust. Okay, let's try importing some information. And the way to do that for elevation is through import contours. If you import just through import through a DXF or DWG, you won't have the opportunity to assign a particular layer to elevation. So it's necessary to use import contours. And we can see down here in this drop list that we have options: DXF files, Esri shape files, CSV files, or KMZ files from Google Earth. We'll choose CSV files, which are text files, and these might be typical files that come out of GPS units or survey equipment, or from processing from various sources. When we click on that, there is a preview, and you can see right at the top that there are 4 columns of information. There is an identification number, there is a X, a Y, and a Z. And you can see that the Z is 8.5, and then it goes to 12, and the identification number changes. So that's an indication that perhaps these are contours, that the ID 1 and the same elevation is a contour. So we are going to import that. And the first thing we do is have to specify the order of those parameters. And from that preview, we could see that we had the identification, the X, Y, and the Z. And here are the other options that are available. We have the option to import as polylines. It has detected that perhaps there are some contours there. That is the layer. We get a message saying maximum and minimum elevation and the coordinates associated with those elevations. And now we have 3 contours. And if we double click on those, we can see the elevation, 12. I think we saw that one of them was 8.5, maybe this one down here. Yes. We can try that process again. We know that it's ID XYZ. This time I'll remove the check on import contours. And now we can see the points. So there were points and in that file using the previous message, we imported contours only. We repeated it and imported the text. Okay, we'll try another method, and this time we will import contours. And again, it's important to use import contours. And we need DXF files or shape files or CSV files. We can't import contours from DWG files. But so we will go to the DXF file and we'll import this example contours file. This is the layer in that DXF file that has the contour information. IRRICAD interrogates the file and comes up with this message. There is a maximum elevation of 1,249 feet, a minimum elevation of 0 feet. The X and Y coordinates for the maximum elevation are very large, and the minimum X and Y coordinates are 0, 0. So that's a little bit of a red flag, and it's important to pay attention to this message because it will give us clues to what to do when we import the file. So I'll click on OK, and it's difficult to see where things are on the screen. And in fact, sometimes things are so separated that you see absolutely nothing, and it can be difficult to find out what's there. But I know from experience with this particular file that here is the field up here in the top, and the origin of this survey is down near the bottom left. And that's what's causing our 0, 0 with 0 elevation points. So I'm going to use select window because sometimes there are multiple points over that same point, and I'm going to delete those points. And then I'm going to use zoom all, and we see the contours. So keep an eye out on that message when you import contours. If the distance between the minimum and maximum elevations is very large, then the origin for the survey has probably been included in the file, and you'll have to hunt for the origin and delete it. We can produce the DEM again. I think my computer's moving a little slower because it's connected to a lot of people viewing at the moment. This normally takes 10 seconds or 15 seconds.
Hutch, if you would like, we do have one question that maybe about that from Marcio. It would be like exporting a digital elevation model generated in the Aircad in DXF, but it contains elevations. Is that maybe relevant to the steps you're in now?
Exporting the digital elevation model, I'm not sure that we can do that. Let me check with Joe at some stage, but at the moment I haven't found a way to export the digital elevation model. It can be saved as a picture included on the design, but I don't know how to. I don't think there is a way to export those actual virtual points in the background to a different file. So there we have the elevation, and we can see that everything looks pretty good. What I'm going to do now is change the elevation of one of the contours. And because it took a little bit of time, I won't generate this digital elevation model again, but I'm going to change an elevation to be much, much lower. And what would happen is that this model would end up with a huge crater in it. And so if you see a model that has a huge crater, then you know that one of the points is not valid. And what I'll do there is go to this point here, and it's 1,224, and I'll change it to 2,224. The next one is 1,225. So we know there's an error there. When you generate the digital elevation model, you'll see a huge crater in it, and that's an indication that there is an error in the data, and that's one of the benefits of producing that digital elevation model. So we'll create a new design and elevate and import some points. And we'll use this file here. We want to import the points. Here we have the minimums and maximums, and we have the points. Quite often when I import points, I will migrate them to another layer. And so to do that, down in the bottom right, I'm going to create a layer called survey points. And I'll create that layer, and here it is here. Now I'm going to select all those points and right-click over this layer and move them to that layer. So I can turn that layer on and off, and the points go on and off. Now I'll generate the contours. And let's say the contour interval is 2, and we'll generate the contours. And the reason that I migrated those points to a separate layer initially is now I have the opportunity and the ability to turn them off. If I did not do that, both the points and the contours would be in the elevation layer, and really I want to visualize the contours. I don't really want to see the points. And we also have the opportunity to highlight the elevations, which will give us a color scale of the contours, which better gives us a better indication of what's going on. There were some other things in that file that we may want to import. And so what I'm going to do is go through the import process, not the contours. I'll select the same file, but in this case, it's just going to import all the data as lines. And we can see that we have different layers here. We have a boundary layer. I don't need the points layer, so I'm going to delete that one. I don't need that layer there. I'm going to delete that one. I'm going to turn the elevations off and the boundary off. And I'll delete those points. And so that's a way to bring in information other than the points that you created. Okay, what's up next? So next we're going to import what's called a shapefile. And we use the same process, and shape files come from the Esri platform. And so down here, we're going to select the shape file, and we'll select this one here. The elevation layer we want, and we want all of these because these are major, minor, and intermediate contours. Again, we have our maximum, minimum information. And we can see that we have the contour lines. We can also see that the X and Y coordinates are very large. So most likely, this is geo-referenced, and the coordinates are very large. I will draw some mainline pipe in here, maybe some 6-inch pipe. Okay. Let's say after importing this this design, and you've done a design that you want to view it in Google Earth. So we can go view in Google Earth. And we get an error message that there is no UTM zone specified. So this is an example where there are large coordinates, and these coordinates may exist in multiple UTM zones. I know that this field was close to Walla Walla, so I can go into the settings, into grid, and I can specify the UTM zone that this came from. And so now if I want to view that in Google Earth, it will have the necessary information to know where it is in the world, and we can see it. Normally we would leave the UTM zone as 0. If by chance you do set it and then save as defaults and then import data from a different area, you could get a confusion of zones. And normally you will get an error from IRRICAD if that happens, but sometimes you may not. So as a default, leave it as 0, and then if you need to set it there. Before I show you this in Google Earth, I'll show you one more feature that is useful. I'm going to draw a point, just a standard point down here. And then I'm going to obtain the information from that point. And we can see that the X and Y coordinates are very large. I'm going to copy the X, and then I'm going to go to settings, back to this grid origin, and in the user origin, I'm going to paste that X value. I'm going to copy the Y value, go back, paste it there. Now I'm going to activate my user origin. Now what that does is, now you can see the coordinates in the bottom of the screen. Everything is in much more usable coordinates. This point here has become 0, 0. And so if we draw 1,000 feet of pipe, our D value in the command bar will be 1,000. And the coordinates will be relatively low. You can turn that off at any time, but it's a really useful tool when you're working with geo-reference coordinates to have numbers that are more easily to recognize and to follow along with. So now we will view this in Google Earth. And what I'm going to have to do is stop sharing my IRRICAD screen and share my Google Earth screen. And you should see the Google Earth screen now, and with that, those contours and those pipes. And that's one of the results of geo-referenced information. And that shape files by nature do not have the UTM zone. So we saw the error message created by that. I put the UTM zone in, and then that enabled me to view it in Google Earth. And our next session is on Monday, and Vivier will be going over in depth the import from Google Earth, the view in Google Earth, and the setup of the API key for Google Earth. So that concludes this session on IRRICAD. The next one will be importing from Google Earth on Monday, January the 11th at 11 a.m. Pacific USA time. I hope this session has been of value, and we will see you again on Monday. Thank you very much.